Okay, thank you very much. Thanks, Scott. Hello, everyone. My name is Weicheng Zang, a senior postdoc fellow from Harvard and Smithsonian. Today, I'm going to introduce the progress of the KMTNet AnomalyFinder and the Mass-ratio function. I want to mention that there's a large team supporting my work showing this talk. Here, I can only acknowledge the main members, including the PIs of the KMTNet microlensing survey, Cheng-Ok Lee, Cheng-Ok Han, Andy Gold, and also my mentor at CFA, Jennifer Yi, and also my PhD supervisor, Shuzo Mao, and the new postdoc at the Westlake University, Hong Jingyang, who made great contributions to the KMTNet data reduction. First, let's go back to 9 years ago. 2016, I think, is a very important year for the microline planet search. First, the Moore survey published its statistical sample of 22 planets based on the by-eye search for the planetary signals. It is found that the number of microline planets increases while mass ratio decreases, following a power law, until a break about 1.7 times 10⁻⁴, below which the occurrence rate likely drops. One reason for this break is that there are 8 planets between the log mass ratio, -3.7 to and -3.0, corresponding to the mass. Okay, the mass, not the mass ratio. The mass of about Saturn and sub-Saturn. In the meantime, another team led by Yossi published a sample 8 planets based on an algorithm-based search for planet signals, which only had 1 planet in the Saturn and the sub-Saturn range. In addition, the 2 samples together only have 3 planets with a mass ratio below 10⁻⁴ and no planets below the Uranus to Sun mass ratio. So we need a more powerful microline survey to study the low end of the mass ratio function and also to resolve the conflict in the Saturn and the sub-Saturn range. In the same year, the Korea Microline Telescope Network, KMTNet, began its regular survey. KMTNet has 3 identical telescopes within field of view of 4 square degree in Chile, South Africa, and Australia, while other surveys only have 1 telescope with a smaller field of view. So KMTNet should have a much higher sensitivity for low mass ratio planets. But 4 years later, at the end of 2019, with the by-eye search, there were still no planets below the Uranus to Sun mass ratio. Things have changed since I built the KMTNet AnomalyFinder pipeline. It was complicated, but the basic idea is simple. For most microline planet events, the residuals from single lens model can be fitted by a flat curve with short allowed deviation in some places. So I first fit the KMTNet data with a single lens model, extracted the residuals, and then used a single peak model to match and locate the short allowed deviations in residuals. With the AnomalyFinder, many buried planetary signals were found, and we conducted the first mass production of microline planets and made a series of papers named Systematic KMTNet Planetary Anomaly Search. For the first 12 papers, we systematically published 53 clear planets and 16 candidate planets. The Chinese team is highly involved in this work, including 50% of the analysis and the most publication level image reductions. In this figure, the black dots represent the number of published microline planet events every year. The AnomalyFinder paper was published in October 2021, and then in 2022, 49 microline planets were published within 1 year, increasing the number of microline planets by 50% within 1 year. Up to date, of the about 230 microline planets, 180 were led by KMTNet. With this mass production approach, we have formed a sample of 101 planets, which is 5 times larger and it reaches a mass ratio n order of magnitude lower than any previous microlensing studies. In this figure, the histogram shows a mass ratio distribution of this sample. If we only show a planet identified from bi-search as this red histogram, we can see bi-search is almost sensitive enough for massive planets, but miss the half of the low mass ratio planets and the most planets below the Uranus to Sun mass ratio. So without the AnomalyFinder, there may be a break between 10⁻⁴ and 10⁻�3. And we corrected the distribution by the detection efficiency of KMTNet data and my AnomalyFinder pipeline. The blue histogram represents the distribution of the real planetary frequency. The three blue arrows indicate the 1 sigma upper limit on the mass ratio bins without a planet detection. Overall, this distribution is well described by Apollo, and we don't see a break at 1.7 times 10⁻⁴ proposed by the Moore survey. We can see three dips in this distribution, one around the brown dwarf and super Jupiter, one at the Saturn and sub-Saturn region, and one at the Earth and sub-Earth region. So we also fit a double Gaussian function and found the distribution is better described by two populations with peaks at 7 times Earth to Sun mass ratio and 800 times Earth to Sun mass ratio. The two peaks could reflect differentiation due to the underlying planetary formation process. The first peak represents a population of gas giants with a frequency about 50%, consistent with the result from the radial velocity study. And the second peak represents a population of super Earth and mini Neptune with a frequency about 50%, which could be the field cause of gas giants. And the dip between these two peaks could be a signature of the runaway gas equation. If we also plot Moore's broken power law function in this figure, a dramatic difference is at the, we can say that is a Saturn and a sub-Saturn region, as proposed by Dave. In this figure, I show the rate of Saturn and sub-Saturn planets for 5 statistical samples, considering they have enough sensitivity for mass ratio above 10⁻⁴. Besides the Moore sample, the planet and the microphone sample also show a high rate of such planets, while the sample from the Y survey has a low rate. But these three samples were limited by small number statistics. Even the difference between Moore and the KMTNet samples are only about 2 sigma. So the difference may be caused by the statistical fluctuation. Actually, the biggest difference between KMTNet and Moore is for planets below the Uranus to Sun mass ratio. As far as I know, Moore didn't detect any such planets from the 70-year survey, leading to a 1 sigma upper limit of about 5% per star using the Suzuki sensitivity, while the KMTNet sample has 10 such very low mass ratio planets, and most signals have the confirmation from the Ogle and Moore data, leading to a frequency an order of magnitude higher. In the next talk, Suzuki will show the combined sample of KMTNet and Moore. I'm wondering whether we can combine two samples if they show very different features. Let me give you one example. 14 years ago, Moore indicated that there are 1.8 free-floating Jupiters per star. 7 years later, Ogle suggested that no large population of free-floating Jupiter using a sample 6 times larger. If we combine these two samples, there are still about 0.4 free-floating Jupiters per star, several times higher than the frequency of bound Jupiters. As we all know, many years later, Moore excluded the large free-floating Jupiter population. So in my opinion, if two samples have very different features, we should be very careful about the combination, because such action will include systematics anyway, no matter whether the systematics come from KMTNet or Moore, and especially that one sample was from the bias search and the other was from the algorithm-based search. To me, the most curious result of the KMTNet Mass-ratio function is that we only detect one planet with mass ratio below 10⁻⁴, 10⁻⁵ from the 8-year KMTNet survey, while the power law function suggests one such planet per year. Of course, we may overestimate KMTNet sensitivity for such planets. How about Roman? Can Roman detect many such low mass ratio planets? Based on Matthews simulation, it is suggested that Roman can detect about 1,400 microline bound planets. However, the planet frequency obtained by KMTNet and Moore are both much lower than the input in frequency used in the prediction. And the Roman can detect about 600 planets. For planets below 10⁻⁵, if the Moore broken power law function or the KMTNet double Gaussian model is correct, Roman can only detect 6 cases. So hopefully the power law, the KMTNet power law function is true. By 2028, our KMTNet will form a sample of 400 planets. If the additional 300 planets show the same distribution, we expect to have a 8 sigma significance on the Saturn and the sub-Saturn region, and a 4 sigma significance on the Earth and the sub-Earth deep. More importantly, we can anticipate more features revealed by the larger KMTNet sample to infer more about the underlying planetary formation process. Okay, that's all my talk. Okay, Scott, I have added my talk.
What was that? Okay, we have time for one question.
So I think your presentation overestimated the sensitivity of the KMTNet survey a little bit by a couple different ways. First of all, when you're looking at mass ratios above 10⁻⁴, you're using half the time times half the years of the you twice as many years for finding events for mass ratios below 10⁻⁴ than above 10⁻⁴. So in terms of the number of detections, it might be better to just use the consistent number of years for the sample. Also, perhaps more significant is that in the comparison of the Zucchiol sample to population synthesis models, we were comparing to a prediction that it was mass ratios between 10 times 10⁻⁴ and 3 times 10⁻⁴. And that was something, a mass ratio range that was set before the calculation. But here, you're picking a region after looking at the data. So that's an example of a posteriori statistics. So, if you've got, 12 or 15 bins, so the odds that you have an outlier in one of those bins, to the power law model is a lot higher than the odds that you have an outlier in one specified bin. So, and also I should say that, the error bars that Noah got on the low mass ratios are quite large. And, you know, we didn't show that it was actually a peak. We claimed it was a break. But even then, the Bayes analysis or Bayes factor of was marginally significant. So, so it turns out to be, you know, just a straight power law. You know, it's only violating, you know, a claim by Moore that's of marginal significance.
Sorry, I lost the track of your on your comments, but I think we can discuss it later. And
Okay.
yeah, Scott.